Good afternoon, ladies and gentlemen. My name is Matthew Brooks. This is Drew Taylor, Jesse Krigelman, and Lee Chavous. And today we're presenting our senior design project on EEG-Driven Peripheral Computer Control. And our faculty advisor advising this project is Professor Dr. Iyad. Now, many of you have heard of EEG technology before. It's been used for the past couple of decades. The concept of basically putting electrodes on a user's scalp and measuring brain signals that are happening from electrical activity below. It's been used mainly in the medical field for the past couple of years. And pretty much what is happening is that with the advancement of computer technology and digital signal processing, we can now actually do advanced analysis on these signals and correlate them to elementary brain functions. Now, this has been done for the past couple of years in laboratories requiring expensive equipment, experienced lab personnel, and it's far out of the reach of the hands of consumers. What they're doing now with current brain-computer interface is correlating these signals, like I said, to elementary brain functions and using it to control prosthetic limbs for the physically disabled, and even the control mouse movements, for example, which is the primary interest of our project, is to use brain signals to actually control the mouse cursor on a computer. What we've proposed to make is an alternative to what's going on in the lab and bring it home to the consumer. We've set out to make a brain-computer interface that's affordable, smaller, and self-auto-calibrates itself to each individual. And this will be compatible with all ordinary standard desktop hardware and software. Here's the main layout of our design. We basically have an EEG cap, scalp electrodes, which is wired into our signal acquisition plate. Right there, the metal box. That's where all the amplification of the signals takes place and the digital sampling. Once it's digitally sampled, it's then piped into a standard desktop computer via standard digital serial line interface. Then our software takes care of the advanced digital signal processing and turns into 2 axes of freedom. We had a sample video of 3 trials that we have in the lab. This is a subject wearing the electrode cap, where we have 2 electrodes only wired up with the sensory-motor cortex in the back of the brain right here. And we have an instructor in the lab that's actually instructing this person to move the cursor to the upper and lower extremities of the screen. Now, of course, there's a couple seconds of lag due to software, and there's also, you can see the cursor right here going up and down. We only have 1 axis wired up. And there's a couple seconds of lag to the software, but it's also very erratic. After a couple seconds, the user will then finally get into the desired position. Now, how did we do this? How did we control the mouse cursor with 2 electrodes? I'm going to have Drew talk about the hardware.
Thank you, Matt. The hardware for our project consists basically of 2 main parts. We have the headgear, which is the electrode aspect, and then we have signal acquisition equipment. This is responsible for interfacing to the user's computer. Okay, the headgear, or the electrodes, are placed directly on the user's scalp, and this is required to conduct EEG signals back to the signal. The electrode placement scheme that we're using is the standard 20 system. However, we are only using the P3 and P4 regions, which are shown here in the diagram. In addition to these 2 electrodes placed on the user's scalp, there are also 2 reference electrodes on the heels. Okay, initially we had experimented with individual electrodes using a homemade cap. And this didn't work too well because we could only do 2 electrodes at the most, and it was very time-consuming to apply, relatively inaccurate. The electrodes kept moving around. So the final solution we came up with was an electrode cap. Now this is a professionally made clinical EEG cap. The electrodes are permanently attached in a 10-20 arrangement. This aids in the application. It speeds up applying the cap every time the user wants to put it on. It also helps with the accuracy because the electrodes are permanently fixed in a position. In addition to this cap shown here are the rear clip electrodes. Now these are used as ground reference points. This is connected directly to the amplification. All right, the signal acquisition equipment that we're using is the Open EEG system. This is an open source hardware and software project that we chose. It consists of one digital board, which is basically a signal sampling system, and 3 analog amplifier boards. Now, we chose this project primarily because it's constructed of relatively inexpensive and available hardware, which was very important to our project. And also, the full documentation for the system is available online, such as schematics and parts lists. And that was also very helpful for us. Now, this is a block diagram of the Open EEG system. This shows 2 channels coming in at the electrodes here. The signal first goes into an initial amplification stage, where it is then passed to a second amplification stage before going through a low-pass filter, which removes any 60 Hz AC noise that can get coming through the electrodes. From the amplification stages, it's passed on to the microcontroller, where it is acquired, and sent into the serial line, where it's finally sent to the user's computer. These are just a couple of basic specs for the EEG system. Input voltage resolution is 0.5 micrograms. Full scale voltage is plus or minus 256 micrograms. We constructed the Open EEG system completely by hand. We used discrete parts and printed circuit boards that were separately. We made a couple design modifications to the hardware along the way. We expanded the system from 2 channels to a maximum of 6 channels. And this was supported by the AVR microcontroller that we used, which has 6 onboard analog to digital converters. Also, it features a UART for serial communications, all contained within the microcontroller itself. Okay, the computer interface protocol is a standard RS-232 system. It's opto-isolated for safety concerns. And it also supports a baud rate of 57.6 kilobits per second. And this is well enough to support our 256 Hz sampling model. Shown here is a serial packet structure. Now this is an 11-byte packet. It's segmented into several parts. First we have the header, which is the first 8 bits. Then we have the auxiliary channel, which is not new to this. This is the firmware version, but it's for future expansion. Then all 6 channels of the data are sent. Now each channel has 10 bits of resolution. So it's broken up into the first 7 bits for the first channel, the first 8 bits for the second channel, and the remaining 3 bits of each channel. And that structure repeats. The second design modification we made was the addition of USB connectivity, and this was necessary just to ensure compatibility with all modern computers. Now, once the signal gets into the computer, it is then processed by our software, and to talk more about software, I will turn it over to Jesse.
Hello everyone, Jesse, in charge of software. And this project we had a pretty big undertaking. It's very complex, and in order to try to figure out the best solution for our given time frame, we went with the simplest solution. The simplest solution was to use a linear equation, which was already something found to work amongst the professional community. And so this is kind of the flow diagram of that same linear system. And what's kind of happening here? You guys have all the world data that comes in, coming in time domain, so from the brain, and we break it out into each separate channel. And in particular, we're only using 2 channels, and we do fast Fourier transforms. We pull out frequency data, pull out 12 and 24 hertz for each of the 2 channels. We augment that data with some kind of weighted multiplier. The weighted multiplier comes from another part of the project, which I'll discuss. For now, it's just a multiplier. When it's been multiplied, all the like frequencies are summed together along with some constant, and then it's scalar, constant scalar. And this, after it comes out to the scalar multiplier, we end up with two pointer changes. So it's basically from its current position plus that value will give you the new cursor position. So we're going to try to demonstrate a little bit as to what that equation is really trying to do. We're reading from the brain signal. That signal comes out. We are given two separate signals. As I mentioned already, we're in time frame. In order to process this data, we're going to take in a window of 512 points, and we're going to actually move the window 32 points at a time. There's probably a better setup for that, but for the time being, we decided that was probably the best way to go. We just stick with one value and keep on working with it. So once we get the data, put in frequency data, we eventually end up having the whole entire array of frequency data that goes out. But for this particular thing that we're doing right here, even though the two signals are coming out, two different amplitudes, we hope that, or we know that our two weighted values, two multipliers, we're going to help try to correct for the two differences in the signals and make them equal, and then flip them. And by doing so, we're able to get a whole entire array of values, which in this case, two signals cancel each other out, giving us no cursor. So that's something that we would hope that you can accomplish, but obviously your brain's not going to produce perfect sinusoids, and you're also not going to always agree with one another. Eventually your brain will figure it out. So what we're going to look at right now is what if the brain were to increase the amplitude on one side, one hemisphere of the brain. In this case, it's going to be a left hemisphere. Now we get our new data. In this case, we just happen to double the amplitude of the signal that came out. This once again is sensitive. We go to find a black box. The equation comes out, and with a new array of values. In this case, now the pointer is trying to be pushed down the screen because this is 24 hertz signal, which is moving the vertically. Vertically, we're moving down. And just to kind of like bring home, now we're going to increase the amplitude of the right side of the brain, which gives us the 500 on the right, and we're taking the 150 that we started with. Going back to the black box again. Now we're looking at the cursor position being pushed up the screen, which obviously is down. One of the interesting aspects of this project is that this equation alone is not enough in order for everything to work as a whole. We also have to have a point where it's going to adapt itself. It has to, while the person's trying to learn the system's trying to learn the person. Now, in order to use that, there's a lot of different ideas, a lot of different papers that try to argue different points of what's best. And what I went with was what's best in order to make it work and also keep up within our time frame. So I used the least mean square, which is a linear regression algorithm. I usually use it in order to find the direction of best fit for a line of data that's kind of scattered around. Once the least mean square algorithm is done, it ends up spitting out four weighted values. That's going to affect the 12 and 24 hertz frequencies that we saw back in the first slide. Now this guy's kind of a recap. This is what we're actually looking at, implementing inside C, or we did implement inside C. The only thing that's never really discussed here is the software itself. And one of the reasons I did it was it's probably more boring than what I talked about already. And the only thing that's happening inside C is we're implementing these particular equations, and it's being done in a multi-threaded C environment. So we already seen the linear equation at work in the beginning. Least mean square, they kind of tossed under the rug in the system's equations is what's going to actually solve these things for it. So the program itself, however, actually has this equation written out just this way. And I'm just working on that to go with you a simple set of equations. In order to kind of show how we got to the results that we did, we'll leave it to Lee in order to discuss that.
Or we could go ahead and begin working on the software that Jesse talked about. We needed a tool to calibrate and test our hardware. We chose to use an open source software package called BioEra, which is available for Windows, Linux, and Mac OS X operating systems. It uses integer math for increased speed, and it has tools such as fast Fourier transform, filters, oscilloscopes, things like that. Another thing that led to our good results that we thought was worth mentioning was our organization that we had for the whole year. We made this group wiki back in during the summer of 2007, and it was a great way to organize any of our results and anything that had to do with our project. Any of our members could log in at any time and edit material or upload things throughout the semester. Since we're working with real human beings, we needed to think about safety and health. So we chose to do all testing on individual group members only. And our circuit had opto-isolators incorporated into the design to shield the subject from any power surge. And by testing on ourselves in educational setting, we became exempt from any health or safety review from organizations like the institutional review or others like that. And our budget in the university was $300. The analog musical boards that Drew just talked about came to about $70, and the converted to populate them came to $190. The prefabricated electrode cap was purchased by our advisor for future lab research, and the total cost came to about $720. There was a couple of things that we needed along the way, like the metal box and the supplies and things, and we paid for that out of our pocket. And finally, here's a breakdown of our time schedule. You can see we started for the summer 2007, and once that was completed, the initial research, we were able to begin building the hardware, which was done at the same time as the software development. And once that was completed, about 2 months ago, we began testing and calibrating the hardware and software adjustments. And now Matt's going to talk about our conclusion.
So we basically, at this stage of the project, have successfully demonstrated X and Y axis cursor movement. The thing is, one of the major roadblocks we ran into is getting the user to modulate both axes at the same time. So at the current state right now, like you saw in the video, we have the vertical going. You can also flip that onto the horizontal axis and have that move, but not at the same time. We think with the inclusion of this threshold algorithm we've been working on, that would be much more improved, and the user, through the use of more training, would be able to do that. Since we're also tapping off the sensory motor cortex, the back region of the brain, which is responsible for physical muscle movement, is also stimulated when you are imagining physical muscle movement. So this is sort of unique to each individual. Some individuals have to imagine other physical activities in order to modulate the mouse cursor. We found that the most successful solution is imagine that you're on an inclined surface and you're correcting for your balance. So if you are on, let's say, a boat that is rocking, or a skateboard that's on a right, rocking to the right, you correct your balance to the left, the cursor would go one direction, and vice versa for the other direction. This is what our software currently looks like at the present state. It runs in like a command line DOS-like window. It doesn't have a GUI. It will change the normal Windows mouse cursor up and down, or horizontal. We do have a graphical user interface for our configuration value. We have default values set. You can just run the software and it'll take care of itself, and it'll do adaptive filtering. But we have also included this graphical interface for tweaking, and it's been especially helpful in our lab square experiments. We did some experimental GUI interfaces for calibration routines that we originally proposed. I don't know if any of you see that presentation, but there's a lot of different concepts for visually walking the user through almost like a video game in order to tweak all the values of equations that we were using. We already designed and programmed the experimental GUI interface, but due to constraints of time, we did not successfully able to implement it with our back-end processing system. Now, with that in mind, that's one thing that can be improved, but there's a lot of other improvements that we make to this project. If one were so inclined to take on this project and continue it for 30 years, they could use active electrodes, which are electrodes that on the scalp of your head actually have inbuilt amplifiers that would clean up the signal area a lot, and you get probably a lot less mouse control, erratic mouse control. The thresholding algorithm that we mentioned would clean up a lot of erratic mouse control as well. Pattern recognition algorithms is something we did not implement. That is mainly due to constraints of time that we had, but pattern recognition algorithms would help the software better calibrate the different individuals a lot easier and allow you to do a lot more control than just simple mouse control. And like I said, better calibration interfaces. We showed one where we had the squares where we had a user trying to move a cursor to desired blocks that were placed around the frame of a computer screen, and based off of how fast that they were moving or how close they were getting to the target area, we control the beta and mu values on their weights. Like I said, we weren't able to graph it onto our implementation of the processing, but that's one thing that can be improved. I'd like to thank Professor Dr. Obeid for helping fund this, helping this happen, the faculty, and if anyone has any questions. Yes?
Were there any steps you take to prepare the apparatus we use?
Well, for
The headgear.
oh yeah, we have a slide that we made about preparation.
Yeah, there's some procedure for preparing the head cap for use, actually. First, we have to clean the surface of the head with alcohol, and this just helps remove any impurities that may be present. Second, as you can see right here, we have abrasive gel. Now, this is good for removing dead skin or anything else that's accumulated on either the surface of the ear or on hair. Yeah, once the cap is actually put on the head, then we have to put gel into the cap, which is the conductor. And basically this helps lower the impedance of the electrode connection to the scalp. And this has to be done for both the ear connection and the scalp connection. That's pretty much it. It's a rather long procedure, and Matt talked about using active electrodes in future designs, and this will help cut down using gel. So it's speed for preparation. Did that answer your question?
We had 6 ADC channels, but we're using 2.
Right. Initially, we had designed whole system for 6 because we weren't quite sure how many. Channels we would need. And the cap we're using actually is 20 right for this one.
What was the FF2 phase size on the sample?
256 seconds.
For 2 seconds of that.
2 seconds a day.
Spectral resolution was? I don't know.
It should be some number right inside those our final report.
Which LMS algorithm are you using? Why?
This means where it's the one that I already showed on the board. And it's just kind of
domain, the original LMS, or the frequency?
it's based upon all the frequency data. And it's one of the things I was supposed to mention, but I forgot. All of our frequency data is being saved inside the array. All of our results are saved inside the array. So those
keep an eye on it, really.
three arrays are being manipulated at the same time in order to give us new beta and alpha values. Go forward. Yeah. So you just kind of had to take the delta values, or the delta equation, and you stick it inside there, and then you produce the final two equations. The derivative of the error with respect to alpha and with respect to beta, and then use system of equations, which gives you the very last one, which is alpha and beta. You make substitutions for D, F, C, E, G, A, E. Make all those substitutions, and you end up being left with a relatively simple procedure to do it. See. And then the weights get fed back, and the weights that are fed back are used for the next time around. So the next time it processes the data, those weights will affect the final position.
Do you find that since it's on the head and it's connected to the scalp, do you find that the hair messed with any of the results, like the length of the hair?
Yeah, there were a couple questions about that, but we couldn't actually prove that hair length affected the results.
Especially with the paste and gel we're using the prep for.
Right.
Based on your implementation, how much of the potential in this type of technology do you think you can tap into? Or do you find that you think that at any higher level of there's always going to be some erratic behavior that you can't fix?
I mean, there's already, especially like I said about the pattern recognition algorithms that are being done, especially at like PhD levels and stuff. That I mean, they got prosthetic arm movements that are amazing.
We didn't use the best set of equations either. I mean, these are the simplest ones. There are ones out there that I looked at them and my head nearly fell off my shoulders because it was so complex and we just look at it, let alone implement it.